Hello everyone, in this video I'm going to be talking about how to determine in proton NMR when a particular signal going to be a singlet, a doublet, triplet, quartet, and so on. So singlet, doublet, triplet, they are actually the number of peaks that you're going to be seeing in a given signal. So how many signals you're going to get, that really depends on how many different protons you have, and then what kind of signal that's going to be, whether it's going to be a singlet, doublet, that actually depends on the adjacent carbon proton. So how many protons you have on the adjacent carbon, that will tell you how many signals you're going to be, how many peaks you're going to see in a given signal. So if I'm focusing on, suppose this carbon right there, and then I have two protons here, but how the signal of these two protons will show up is actually dependent on the adjacent protons. So the adjacent protons would be, I have three here, and I have three here. So if I talk about how many different signals I have here, this is going to be one, that's going to be two, and that's going to be one again, because remember there's a symmetrical, so this propane, the methyl groups on each side is actually going to be equivalent. So if I talk about carbon, proton 1 and proton 2, so proton 1 is actually going to be the integration of 6 protons. That tells you how many protons you have there. And the signal 2 is going to have 2 protons in there. Now, the next question is, how would proton 1 show up as? So the proton 1 show up or peak will be dependent on the adjacent protons. So the adjacent protons to proton 1 would be the carbon number 2 that has actually 2 protons on it, and we always going to be using this formula called n plus 1, so n being the number of adjacent protons. So in this case, since I have 2 protons, so 2 plus 1 is going to be 3, so that means you're going to be seeing the 3 peaks on this particular signal, and those 3 peaks will show up as a triplet. Now, when I see the 2H, or the second signal that has 2 protons on it, and if I count how many total adjacent protons I have to the carbon 2, well, I got carbon on the left side and carbon on the right side there. I got to count both of those because they're both adjacent, so that gives you a total of 6 hydrogens. So total of 6 hydrogens, and plus 1 gives you 7, so that means there are going to be 7 peaks in that particular signal number 2, and that's going to be actually a septet. So that's what it's going to be called. So this is actually called in a 3-bond coupling. Why this is called in a 3-bond coupling? And from here, that's 1 bond, that's 2 bond, and that's 3 bonds. So there are like 3 bonds away between those hydrogens. So that's going to be the 3-bond coupling. Sometimes you may see the diastereotopic protons. They are also coupling. There are 2 bonds coupling. And sometimes you will see the 3 bonds coupling as well. And that usually happens in case of aromatics. So I'll talk about that whenever we get to those examples. But here, I want to talk about some more simple examples here. So how many different signals I have here? Well, I got 1 proton here. So it's going to be signal 1, and I got 3 methyl groups, and they're going to be equivalent. That's going to be giving you the second signal. So I'll say signal 1 and signal 2. So signal 1 has 1 proton. How many protons you have on the second signal? Well, I got 3 methyl groups, each methyl group containing 3 protons, so that's going to be a total of 9 protons on the second signal. So signal 1 is actually going to be having 9 adjacent protons. So since it has a 9 adjacent proton, it's actually going to be 10 peaks on it. So probably at that point, I probably just say it's a multiptet, because it's going to be very hard to kind of see 10 peaks in there unless you really, really zoom in. But the typical NMR, when they're giving you from 1 to 15, it's not going to be that zoomed in, but there are going to be 10 peaks in there. When I look at second signal that has 9 proton integration, it has only 1 adjacent proton, so that means this will show up as a doublet, or another way of saying there is going to be 2 peaks on that particular one. So we already talked about the number of peaks will be determined by the n plus 1 formula, where n is going to be the non-equivalent protons. If you have multiple non-equivalent protons, then you can use this formula n plus 1 to determine the number of peaks. Now this could be a little bit sketchy sometimes, because sometimes their coupling constants are the same, so you just kind of add them up together and just use n plus 1. But typically, if you're trying to figure out how many peaks you're going to have, you will be using n plus 1 times n plus 1 formula. So let's take this example right here. How many different proton or different signals I'll see here? I'll have 1 here, 2 here, 3 here, 4 here. So technically, I have a total of 4 signals here. Signal 1 or carbon, those methyl groups has 6 protons, so it's integration. Signal 2 will have only 1 proton. Signal 3 has 2 protons, and signal 4 has 3 protons. So that's how you want to look at the integration. Now, when I'm looking at signal 1 that has 6 protons, how many adjacent protons we got on that? Well, only the adjacent carbon you have would be carbon number 2. And carbon number 2 has only 1 proton. That means this signal 1 will show up as a doublet. So it's just clear. This is just what we just talked about earlier. But now let's look at this a signal 2. Now signal 2, which is only 1 proton. Now how many adjacent carbons I got on here? I have carbon 1s to be adjacent, then I got carbon 3 to be adjacent as well. So I have a total of 6 protons on carbon 1s here, and I got a total of 2 protons on carbon 3 here. So they're not really equivalent. Carbon 1 protons and carbon 3 protons are really not equivalent to one another, and that's when we use this n plus 1 times n plus 1 formula to determine the number of peaks. So if I say 6 plus 1 times 2 plus 1, that will tell you how many peaks you're going to have. So 6 plus 1 is 7, 2 plus 1 is 3, so that's going to be 21. So that's actually going to be very hard to kind of decipher if you actually have 21 peaks or not. So a lot of time you just call that a multiptet. Now, sometimes if the coupling constant of these of these carbon 1 protons and carbon 3 protons are the same, then you can add them up together. So in that case, I would have 6 protons on carbon 1s, and I got 2 protons on carbon 2, so that makes a total of 8 protons, and then I can simply use n plus 1 formula, which tells you there are going to be 9 peaks in that particular case, even though they are really not 9 peaks, but just because their coupling constants are so close or they're same, all of them are kind of on the top of one another where you only see 9 peaks. So in that case, that's just going to be a non-it. But either case, I will call that multiplet anytime you have a proton coupling with different types of protons. Another way of saying, I would say, okay, with respect to the 6 plus 1, that's going to be a septet. And with respect to 2 plus 1, that's going to be a triplet. So I can say this particular signal is either going to be a septet of triplet or it's going to be a triplet of septet. Now, whether you call it triplet of septet or septet of triplet, that's something you may not learn in sophomore organic. That's going to be something if you take an special topic organics. But right now, the best way to call this would be the multiptet. I can do the same thing with this proton 3 signal. So I have 2 protons, but then I have how many adjacent carbons I got? I have carbon number 2 and I got carbon number 4. So carbon number 2 has 1 proton and carbon number 4 has 3 protons. So that's going to be, again, n plus 1 times n plus 1. So it's going to be 2, hold on, it's going to be 1 plus 1 times, that's going to be 3 plus 1. So if I multiply them up, so it's going to be 4 times 2, that's going to be 8. There's going to be 8 peaks in there. Or another way of saying, I can say 1 plus 1 gives you doublet, 3 plus 1 gives you quartet. So it's going to be either a DQ, doublet of quartet, or it's going to be a quartet of doublet, depending on whichever coupling constant is bigger that comes first. Now, the better way of saying it would be just the multiplet. So that's another thing you want to keep in mind. So signal 4 has only 2 protons adjacent, so that's just going to be a triplet. So that's an easy one. If you have an equivalent protons, they're not going to be coupling with one another. Like in this case, in ethane, Someone may wonder, okay, I got 3 protons on one carbon, 3 protons on another carbon, but remember, both those are equivalent, so they're not going to be coupling with one another. As a result, the integration is going to be 6H, and they're all going to be singlet because they don't have any adjacent protons. So 0 plus 1 will give you the singlet there. Remember, even though it seems like you have 3 adjacent protons, but they are equivalent. Equivalent protons do not couple with one another. Same story with the cyclohexane. You will see a total of 12 protons there, and you will have one signal in there. Everything is just going to be a singlet there. Same story. I got 6 proton on this aromatic, and then they're all equivalent. They're not going to be coupling with one another. You'll see only one signal, and that signal is going to be the singlet. So this is how you're going to be looking at the protons when you're trying to figure out when it's going to be doublet, triplet, quartet. And obviously there are going to be some complicated stuff, especially when you have things around double bond. And I'll do have some examples when you looking at this table here. So let's look at this practice set here. And it's probably going to be a good idea if you can pause the session and maybe do this on your own and see if you got those right. So the number of signals I would have in this first example would be 1, 2, 3, 4, and I have the proton on the oxygen as well. So I got a total of 5 protons there. 1, 2, 3, 4, and 5. So how many protons I have for the signal 1 here? That's going to be 3 protons because that's just a methyl group. For 2, it's only 1 proton. For 3, it's got 2 protons. 4 also have 3 protons. And then 5 is only 1 proton because it's just an alcohol. Now, what's going to be the multiplicity, whether it's going to be doublet, triplet, and so on. So carbon 1, or the signal 1, protons has only carbon 2 to be the adjacent, and has only 1 proton on it. So since it has only 1 proton on it, using n plus 1 rule, this is actually going to be a doublet. I'm not really going to write down the full name, but just the code. So doublet is going to be the D there. If I look at second signal where I have how many adjacent protons, I got carbon 1 to be adjacent, and I got carbon 3 to be adjacent. And then I also have this oxygen that's adjacent, that bearing the proton. But remember, oxygen or alcohol protons generally do not couple with the carbon protons. So that's going to be holding true for sophomore organic chemistry. If you take maybe a special topics, you may see every once in a while where the alcohol protons are coupling, but usually the alcohol protons do not couple with the adjacent protons. So I'm just going to be focusing on the protons that's on carbon 1 and carbon 3. So carbon 1 has 3 protons and carbon 3 has 2 protons. So that's really going to be a multiptet. I can't really call this, I mean, if I add those hydrogens up, considering their coupling constants are the same, so 3 plus 2 would be 5, and 5 plus 1 would be 6, so there would be 6 peaks, calling him a sextet, but I don't know if their coupling constants are the same, and their peaks would be n plus 1 times n plus 1, and that would have been 4 times 3. That would have been actually 12 peaks in reality. And so rather, I'll just call that multiptet. And I also talk about a chemical shifts here, which means like where those protons really going to show up close by. So rough ranges, methyl protons, if there's nothing close by, it usually shows up around 1. So I'll say 1 ppm. This second proton here, on the second signal, it's actually next to the oxygen atom. So if it's next to the oxygen atom, it's oxygen atom being more like a negative, this second proton is going to be de-shielded. So as a result, it's going to be somewhere around 3 to 4 ppm. And then I got this third signal. So third signal also has proton 2 and proton 4. So that's going to give you a multiplet again. And that's going to be somewhere around 1.2 to 1.5 because it's just a methylene proton. Number 4 is in another methyl proton. It has only carbon 3 to be the adjacent where you have 2 protons, so that's going to be a clean triplet, and that's going to be again around 1 ppm. So sometimes they do overlap where it makes it harder to kind of figure out the multiplicity. The OH doesn't really couple with anyone, so it's just going to be a singlet. And the OH protons, they do fluctuate, so they will show up anywhere between 2 to 5 p.m. So remember, the alcohol protons fluctuate where they could show up anywhere between 2 to 5. Okay, what about this next example? I'm going to try to do this as quickly as possible because I got so many here. There isn't a plane of symmetry on this molecule, so right here. So that means the left side and the right side protons are going to be equivalent. So when I'm looking at, I'm going to call this 1 here, call this 1 here, call this 2 here, call this 2 here, call this 3 here, 3 here, 3 here, and 3 here. So there's only technically 3 signals, or 3 different types of protons you have. 1, 2, and 3. So the integration on 1, I got 2 protons on each side, so that's going to be actually 4H. The integration on 2 is going to be 2H, because remember there's 1 proton on carbon number 2 off each side. And then I have 3 here, that's going to be 4 methyl groups. So 4 methyl groups going to give you a total of 12 protons. So that's going to be 12 integration. So multiplicity, carbon 1 has adjacent to be carbon 2. It does have a carbonyl carbon adjacent, but the carbon does not have any protons on it. So carbon 2 has only 1 proton on it. So that means it's going to be only a doublet. So don't count it twice. When it comes down to multiplicity, you only focus on one side of the molecule and figure out how will they show up as. Integration means you have total protons in the whole molecule, then you got to look up everything. But there are going to be times when they try to be sneaky and tricky in the NMR questions where they only give you the integration for half of the molecule, and in that case, they may have said signal 1 to be 2H, signal 2 to be 1H, and signal 3 to be 6H. And how do you know if it's going to be doubled up or tripled up? Well, you're going to have to look at the molar mass in that particular case. But try to keep things simple momentarily here. So carbon signal 1 is going to be a doublet. Signal 2, okay, so there's a few things going on. I got 2 methyl groups, those carbon 3s around the carbon 2, and then I got carbon 1 as well, so they're all adjacent to carbon number 2. So I have a total of 7, well actually I have a total of 8 protons. So it's going to be hard to figure out what exactly the peak or multiplicity going to be, because they are being coupled with non-equivalent protons. So I'll just call that multiptet. And then you have 12 protons. These 12 protons, or these methyl groups, they are next to the carbon number 2, which has only 1 proton. So that's again going to be a doublet. Now, as far as the chemical shifts go, if you have a carbon that's next to the carbonyl, like in this case, it's going to show up anywhere between 2.1 to 2.4-ish roughly. And then this 2 is just a methine proton, so that's just going to be somewhere around 1.5 to 1.8 chemical shift. And these methyls are very far away from those carbonyls as well, so that's going to be somewhere around 1 ppm. So that's going to be their rough chemical shifts. You may want to memorize the chemical shifts roughly of all these all these hydrogens when they're around special function groups. What about this next one? I got 1,2-dichloroethane, so I got 2 protons there, 2 protons there. Well, it turns out there is an internal plane of symmetry, and since there is an internal plane of symmetry, the left side of the molecule is the same as the right side of the molecule, so there's actually going to be only 1 signal. So 1 here, 1 here. So it's only 1 type of proton that's going to be the integration for 4H. And they may also say 2H if they are representing only half of the molecule. Since they are equivalent, and even though they are adjacent to one another, but they are equivalent, they're not going to be coupling with one another. So this is just going to be a plain singlet. And the chemical shift since they are next to the halogen, so halogen being chlorine, bromine, iodine, and even fluorine, that makes them a little bit deshielded, so they're going to be anywhere between I would say 2.5 to 3.5. So these chemical shifts ranges may be a little bit off from book to book, but that's their general ranges for those chemical shifts. Okay, what about this next one here? So I got this double bond now, and let's call this one here. Uh, these carbons that are double bonded, they don't have any protons because they already have 4 bonds. I got 2 protons here, and then I'm gonna call this 3 here, and call this 4 here. Typically, the protons on a cyclopropyl group, like in this case, cyclopropene group you have here, those protons don't really show up together just because one of them is going to be axial and the other one is going to be equatorial. And you can't really flip those that easily. As a result, they will show up differently on the chemical shift. So as a result, I'll call this 5 and call this 6. So another way of saying they are going to be your diastereotopic proton. Now, typically, you'll say the diastereotopic proton will show up if you have another chiral center present already in the molecule, but it's not only limited to the chiral center, but it could be diastereotopic if it's a very small ring, such as this 3-membered ring, and there is going to be a double bond. Well, you don't necessarily have to have a double bond. Sometimes these cyclopropyl group does show up as different protons because they are considered to be diastereotopic protons. So I'll call this 1, 2, 3, 4, and 5. Well, I got a 6 as well, so I'll squeeze that in there. So 1 is 3 protons. 3, well, I don't know why I skipped 2 actually, so I should have been, rephrase those, should have been 2, 3, 4, and 5, so that way I can get rid of 6 there. So 2 is going to be 2 protons, 3 is going to be 3 protons, and 4 and 5 is going to be 1 proton each. So this is 3 protons are going to be your, there's nothing close by because the carbons that are on those double bonded with one another don't have any protons, so there's no adjacent protons to signal 1. So that's going to be a singlet. Signal 2 is, and signal 3, that's actually an ethyl group. So signal 2 has 3 adjacent protons, so that's going to be a quartet. And signal 3 that has 2 adjacent protons is going to be a triplet. Anytime you see a quartet and triplet, typically that means there's an ethyl group there, because the ethyl group is where you're going to have 2 and 3 adjacent protons. And this 4 and 5, you don't really have any hydrogens on the adjacent carbons, but these hydrogens will couple with one another, and those are going to be your 2-bond couplings. So that's going to be your doublet here. That's going to show up as a doublet, and it's also going to show up as a doublet. So typically, if you have a methyl group next to a double bond, that's going to be anywhere between 2 to 3 in terms of chemical shift. Same story with this second signal, that's going to be between 2 to 3. This third signal is going to be somewhere around 1 because it's just a methyl. It's too far away from that double bond. 4 and 5, they're on the cyclopropyl group, but they are also next to the double bond. So I would say, due to the additive effect, because they are going to be a little bit deshielded because of the cyclopropene group, they are going to be anywhere between 2 to 4, I would say, both of those. So this is how you're going to be looking at the diastereotopic protons. Remember, if you have a chiral center, then you can also see the diastereotopic protons in those cases as well. What if you have a benzene ring? What about something like this? I got a CH3 group there, so I'll have 1 here. And there is a internal plane of symmetry where if I draw a line right here, then the left side and the right side of the molecule is actually going to be the same. So if I call this carbon 2 here, this is going to be carbon 2, 2, this is going to be 3, 3, and this is going to be 4. So I'll say 1, 2, 3, and 4. 1 has 3 protons. 2 would have 2 protons, 1 on each side. 3 has 2 protons. And 4 would have 1 proton. Now, the multiplicity, carbon 1 doesn't really have, signal 1 doesn't really have any adjacent protons, so that's just going to be a singlet. The multiplicity for these aromatics is a little bit complicated because they could have a 3-bond coupling, a 4-bond coupling, and even more than that. Or another way of saying they can have an ortho, a meta, and para coupling, and as a result, you can have a doublet of doublet or a doublet of doublet of doublet. So that becomes a little bit challenging. But as a result, I'm not really going to talk about that here. I'll just say all these are going to be multiplets, just because you have all these couplings going on with one another. Now, this methyl proton is going to show up anywhere somewhere around 4 because it's in a benzylic carbon, and then these aromatics shows up anywhere between 6.5 to 8. So all of those are going to be the same. What about this next one? How many signals I would see here? I'll have 1 here, 2 here, 2 here, 1 here, 2 here, 2 here. Because remember, there is, if you can't see it, you may need to practice a little bit more. There is an vertical symmetry and there is a horizontal symmetry. So the left side of the molecule is the same as the right side, and the top of the molecule is the same as the bottom molecule. So there's only 2 signals, and I'll have 1 and 2 here. So 1 would have 6 protons and 2 would have 4 protons. They're all going to be singlets because they're not going to be coupling with the equivalent protons. And carbon 1 doesn't really have any adjacent protons. As far as their chemical shifts go, 1 would be anywhere somewhere around 4-ish, and 2 are going to be anywhere between 6.5 to 8. Okay, what about this next one? I got double bonds now somewhere along the line. So I got a proton here, I got a proton here, and then I got the 4th proton on the oxygen there. So 1, 2, and even though those 2 protons are on the same carbon, but since they are on the double bonded carbons, the environment for these top protons is not the same environment for these bottom protons. All right, so since that's not the same, they are not going to be equivalent, even though they are on the same carbon. So those are actually going to be your diastereotopic protons. Again, even though there's no chiral center close by, but remember your double bonds are also the types of diastereomers where you have cis and trans. So these are going to be non-equivalent protons. So this is going to be 3, and that's going to be 4. So 1, 2, 3, and 4. So signal 1 has integration of 1, so is the signal 2, so is the signal 3, and so is the, oops, hold on. They all have the integration of 1 hydrogen, actually. 1 is an acid proton. They're too far away from any of those, and on the top of that is on the oxygen, so it's not really going to couple with anything, so that's going to be a singlet. This 2 is actually going to couple with the proton 3, and it's also going to couple with proton 4. So it's actually going to be a doublet of doublet, and so is the 3. 3 is going to couple with 4, and 3 is also going to couple with 2. So they are showing the 2-bond coupling and 3-bond coupling. So they're all going to be doublets of doublets in that case, and you may see books calling those multiplets as well. So the acid protons are going to be anywhere between 10 to 12. And these protons that are on the double bonds, they are going to be anywhere between 5 to 6. So how many different signals I have on this one? I got 1 here, 2 here, 3 here, 4 here, 4 here, and 5 here. So 1, 2, 3, 4, and 5. So integration for 1 is just going to be 1H. And integration for 2 is going to be 1H as well. Integration for 3 is going to be 1H as well. For 4 is 6H, and 5 is 3H. So 1 is an aldehyde proton, but the adjacent carbon to that is going to be carbon number 2, and that has only 1 proton, so it's going to be a doublet. Carbon 2, or signal 2, has carbon 3 adjacent, carbon 5 adjacent, even proton 1 to be adjacent. So got too many things going on around it, so I'll just call it multiptet. Carbon 3 again have carbon 4, or signal 3 has signal 4 protons, signal 2 protons adjacent, so that's going to be different types of non-equivalent protons, so that's going to be another multiptet. And 4 is actually having only signal 3 protons to be adjacent, so that's actually going to be only one proton, and that's going to be a doublet. And then 5 also have only one type of protons adjacent, which is going to be signal 2 protons, so that's only one proton adjacent, so that's going to be again a doublet. Where they're going to show up as, aldehydes typically shows up at 9 to 10, and then you have carbon or signal 2 that's next to this carbonyl group, so that's going to be anywhere between 2 to 2.5. And then you got the rest of them just on regular basis. So signal 3 is just in a methine proton, so it's going to be say 1.5 to 1.8-ish. And then 4, just the metal groups around 1. And then 5 is also going to be around 1. They're not going to be exactly at 1, both of those, but these are just the rough ranges. Now, I do want to talk about, I said this aldehyde is going to be a doublet. Sometimes it may not couple with it. So if it doesn't couple with that adjacent proton, even if there is an adjacent proton, then it may show up as a singlet. So something to keep in mind that it may vary depending on whether it's in the plane or not in the plane. Sometimes if it's not in the plane, it's not going to couple with it. This last one I got an amine there, and the reason I want to have an amine there is I talked about alcohol protons where I said alcohol protons usually don't couple with the adjacent protons, but that's not necessarily true for the amines. Amine protons do couple with the adjacent protons. So I got 1, 2, 3, 4, and 5. So I got 2 here. Signal 1 is going to be 2 hydrogens. Signal 2 is going to be 2 hydrogens as well. Signal 3 is 2 hydrogens as well. Signal 4 is 1 hydrogen, and signal 5 is 6 hydrogens. So signal 1, since it's a amine proton, but the adjacent number of protons would be the signal 2 protons. That's 2, so that's going to be a triplet. Signal 2 protons are having adjacent protons to be from signal 1 and signal 3. So that's going to be a multiplet. We'll just say M here. And then signal 3 again have multiple types of non-equivalent protons to be adjacent, 2 and 4. So I'll say a multiplet again. 4 again going to have signal 3 protons and signal 5 protons, and that's going to give you another multiplet. Sometimes they may give you a very clean signal that kind of looks like it's a doublet or triplet or something like that, but typically they're not really that clean unless they tell you otherwise. So 5 is actually going to be only 6 protons, but the only adjacent proton it has would be signal 4, and that's going to give you a doublet in that case. And where will they show up? The amine proton typically shows up anywhere between 1 to 5, so that doesn't really change. And signal 2, since it's right next to the nitrogen, it's going to be anywhere between 2.5 to 3.5 because it's next to the nitrogen, and the rest of them are just going to be as it is. So it's going to be methylene proton is going to be anywhere between 1 to 1.5. Methine proton is going to be 1.5 to 1.8. And then this methyl protons, those are signal 5, are again going to be around 1. So this is a very detailed explanation of how you determining the number of signals and all that. If you have any questions, feel free to leave any comments in the section.